Let's now briefly take a look at our common gate amplifier. And so let me first note that as of the time of making this video, there are no notes for a common gate amplifier on Canvas, but hopefully that's something that I'll have uploaded in the future. So let's take a look at this simple gate amplifier circuit shown on the screen now. We notice that there are a few things different here compared to the previous configurations that we've considered. The first is the actual configuration, or rather orientation, of our transistor. So because we have our gate grounded, and because typically our ground is drawn at the bottom of the circuit, we have our gate towards the bottom and our source and our drain towards the top. So that's a little bit different than what we've seen before. We also have these coupling capacitors CC1 and CC2, which are acting like short circuits to AC signals and open circuits to DC signals. And so we've seen the CC1 before connecting our input, but something a little bit different now is we've included this load resistor R sub L, which again is capacitively coupled with this CC2. So another interesting thing to note is our connections on the gate. So notice we don't have our gate connected directly to ground, rather we have this RG and this CG between the gate and ground. So first let's talk about our RG here. So the reason we have this RG is to prevent static charge buildup on the gate. So prevent static buildup on our gate. And so if we have some static charge on the gate, that could be causing it to turn on or turn off when we don't want it to. And so what we do is, by having this RG connected to ground, we'll oftentimes call this a pull-down resistor. We're providing a path for that static charge to dissipate to ground. So this is our pull-down resistor. However, we don't want that RG to be messing up our small signal gain, our input and output resistance of our amplifier. So what we do is we include as well this C sub G, which is our capacitor, our gate bypass capacitor. And so what we're going to see when we draw our small signal equivalent circuit here in a little bit is that our gate is still going to be at signal ground because our AC signals see this short circuit path through our capacitor C sub G. The last thing that I want to point out that's a little bit different than the circuits we've considered previously is we have this current source IQ. And so this current source IQ is what we're using to bias the transistor in our desired region. And so, as I've mentioned a couple times before, it's actually more common to use current sources to bias transistors than, our voltage divider network or our single base or single gate resistor that we've been using in a lot of our past examples. And so there's a couple reasons for that, and we're actually going to get into that a little bit more in a later class. And what we're going to see is that this IQ, this current source, is actually primarily composed of other transistors. So again, another interesting thing to note, but not something we're going to get into in detail in this class, and definitely not in this video. But we do want to analyze a couple of our common parameters related to this common gate circuit. So we'll look at our input resistance, our output resistance, and our voltage gain. And so in order to do any of that, we need to look at our small signal equivalent circuit. So our small signal equivalent circuit. And so just like we've seen with our other configurations and our other circuits, what we're going to want to do is start with our gate source and drain terminals, fill in our transistor model, and then expand based on what is connected in our particular circuit. So in this case, we have our gate at the bottom, our source on the top left, our drain on the top right. And we notice that this arrow on the source is pointing out, so that indicates that we have an NMOS device. So that's going to determine our voltage polarity of interest as well as our current direction for that dependent source. So let me go ahead and start by drawing our gate down here, our source up here, and our drain up here. So we've got gate, so let me move that over a little bit. So we've got gate, our source, and our drain. And so we know that our gate and source is, so between that we have the voltage of interest VGS, and we also know that we have essentially an open circuit between our gate and our source, and our gate and our drain. However, between our drain and the source, we have our dependent current source. So let's go ahead and draw that guy in here. And so because this is N channel, the current is going from the drain to the source. Now, of course, we could have an analogous small signal equivalent circuit if this was a PMOS transistor. So here, this value of our current source is GM times VGS. And so really that's all we need to do. In this case, we're going to assume that our R naught is equal to infinity. We're going to come back in the next video actually, and we're going to look at a more detailed derivation of our voltage gain using a non-zero, sorry, that should be R naught, a non-zero R naught between our drain and our source. But for now, we're going to assume it's infinity, so we're not going to include it in this drawing. So that's all for our transistors. So now we come back up to this circuit, and we want to start connecting things that are external to the transistor. So as we mentioned, our gate is going to be at signal ground due to that bypass capacitor C sub G. So we can come down here and we can go ahead and say, well, this is going to be at ground. On our drain side, of course, this CC2 is going to be acting like a short circuit. So we have from our drain, we have a path through RL to ground, and we also have a path through RD to ground. And so note that's signal ground because, again, we're deactivating DC sources. So when we deactivate that DC voltage source, it becomes a short circuit to ground. So on our drain side, we're going to have two resistors connected between the drain and ground. And so our ground is at the gate, so we can just extend this over here and connect both of those resistors. So this was our RD, and this was our load resistor RL, and our output voltage is defined at our drain, so we could say that that's V out, or if we want to explicitly show the polarity, of course that's implied to be between that point and ground. So we could write V out in that manner there. Okay, so coming back up here, so now we have this current source, and again, we're deactivating DC sources, but for a current source, if we want to have zero current, we're going to open this current source so that we have zero current. And so what that means is that's just going to be an open circuit here, and so we're not going to have any path there to ground from our source, but we are going to have a short circuit through this capacitor, and then we can go through RSI and VI to ground. So let's come down here and add that to our circuit. So we're going to have this our RSI, which I'm drawing first there, and then of course our VSI, sorry, not VSI, just VI, between there and ground. So we get something that looks like this. Okay, so this would be our small signal equivalent circuit, again, assuming that we have an infinite R naught, and we're going to come back and consider a finite R naught in the next video. So a couple things of interest. Of course, we have our input resistance to the amplifier would be right here. The reason I put it here is we're assuming that this RSI is some internal resistance associated with our input signal. And our output resistance is going to be defined over here because, again, we're not including our load in that. We're just looking at our amplifier. So this would be our output resistance of the amplifier looking back into the amplifier. And so let me go ahead and define some input current here, and so that's going to help us as we define our input resistance. And so it turns out it's quite easy to determine those two values. So for our input resistance, we're just going to have that our Ri is going to be equal to negative VGS because that's the voltage between these two terminals at our input, divided by our current going in, which is I sub I. Now, if we look at that, of course, we can see that our I sub I is just negative GM VGS. So let's go ahead and substitute that in. So we have negative VGS divided by negative GM VGS. And of course, our VGS's and our negatives are going to cancel out. And we're left with our input resistance of this configuration is 1 over GM. And so typically, that's going to be a low value, which means it's going to be not ideal for voltage amplifiers, but it's better if we have a current amplifier. So better for a current amplifier. And there is some analysis in the textbook, so if you look on page 235, there's some analysis where they replace this input with a current input. So they have a current source in parallel with some RSI, and they go through and they do an analysis to find the current gain for this configuration. But we're going to focus on our voltage gain, or rather our voltage input source, and in the next video we're going to look at our voltage gain. But the only other thing we want to look at in this video is that output resistance R naught. And so I'm not going to go through the full details, but we could do something that we've seen before. We could do a test source. So actually, let me go ahead and just write that up real quickly. So we could put a test source here, and again, if we're just doing this in our calculations, this could be a voltage or a current source, so Vx and Ix, and we have to deactivate any of our independent sources. So that means we're going to come over here and we're going to short this circuit, or this VI out. So what we can do then is we can do a KVL over here on this side to figure out our VGS. So let's do that. So we would have that starting down here, going counterclockwise. We could have VGS, and then this voltage drop across here is going to be this current times RSI. So we're going to have plus GM times VGS times RSI is equal to 0, because again, we've shorted out this VI over here. And so what we can see from that is, of course, our RSI is non-zero, our GM is non-zero, so what that means is that our VGS is equal to 0. So with our VGS equals to 0, this is our current source here, so that means we replace that with an open circuit. So if we have an open circuit there, we're essentially ignoring everything to this side of the circuit, and the only resistance that we see if we're looking in at that output is our resistor R sub D. So we can then simply say our output resistance is going to be R sub D. And so in our summary table, you might recall we said that this was a moderate to high value. So moderate to high. And again, that's something that is going to be ideal for our current amplifier. Now, ultimately, our loading effects are also going to depend on what our load resistor are, but we would like to have our input resistance really low and our output resistance really high for a good current amplifier. In the next video, we're going to come back and take a closer look at what our voltage gain is, and then that's going to conclude our discussion on this common gate configuration.